Hi, everyone. So today we'll be going over low voltage DC. And like I mentioned earlier, this is a slide about myself and my background. And this is the agenda for today. So first we'll be going over what is low voltage DC, the fundamentals, decoupling, filtering, load transient, technology key characteristics. And finally, we'll have an open Q&A portion. So what is low voltage DC? This is an example of a low voltage server block diagram that contains CPUs, which have data buses that connect to other circuit blocks, such as digital chips, banks of memory, storage solutions, external I/O devices, and etc. And all of this is within the realm of digital low voltage. Now, most of these systems have a supply voltage, which is much higher than logic level, which is usually 5 volts or less. In the case of a server, the supply voltage could be 48 volts, 15 volts, 12 volts, and etc. And that supply voltage through the system is not the voltage that these digital chips operate at, which is various lower voltages. So this is an example of a power distribution system, which is converting supply voltage, and in this case, 48 volts. This system have multiple DC to DC converters, as you can see, and these are attached to the main power supply, which converts the 48 volts down to the various voltages that are used by the digital chips. Displays, memory controllers, processors, and etc. In this diagram, we have the supply voltage, we have TVS diodes for protection, and then at each DC to DC converter contains input decoupling caps, typically a ferrite or metal composite output inductor, an output filter cap, and output resistors to stabilize the output voltage from the converter switch, which is powering the load. So there are various capacitor technologies, and each have their different capabilities and trade-offs. With ceramics, we've got class 1, which are C0G parts, which are very stable, and these are close to being an ideal capacitor. However, the dielectric constant is very low, so we don't really get a lot of capacitance out of these parts. But again, they are very stable, especially they're very stable across voltage, temperature, and time. Some of these parts can also withstand very high temperatures as well. And then we have class 2 parts, which are XMNRs. And these are made of barium titanate-based technology. And these have much higher dielectric constants. So that means the capacitance range of these are going to be a lot larger than the C0Gs. But these do have some negative attributes, such as DC bias. So putting voltage on these parts will make these parts lose capacitance. And this is just a characteristic of the barium titanate and dipoles and domains within the barium titanate structure. These parts also experience aging, which means that it's losing capacitance over time because of the crystalline structure in the barium titanate, which is changing from a cubic to a tetragonal structure. And then we also have film technology, which have sizes varying from small to large. These do have very low CV density due to its dielectric constant. These, however, are pretty stable capacitors, and they do have self-healing, and they do also have lower ESR. And then next, we have aluminum electrolytics, and these are heavily used in both the input and outputs, as these have large capacitance values compared to, say, ceramics. The downside of aluminum electrolytics is that these tend to have higher ESR, which is tied to the electrolyte being used in these capacitors. And the electrolytes have ions in the solution that has to migrate one way or another, depending on if it's being charged or discharged. And due to this higher ESR, these parts will have capacitance roll-off occur at much lower frequencies compared to other capacitor technologies. These also have a life due to the wet electrolyte, which can dry out. And this is very dependent upon temperature. And we do have a simple rule where in every 10 degrees drop in temperature, you would double the life. And then next, we have polymer technologies, which include aluminum V-chip polymers and tantalum polymers. There are a lot of similarities between these two technologies. The tantalum can provide greater CV density compared to aluminum polymers. The aluminum polymers do offer some larger capacitance values than you can get with tantalum polymers because the parts are much physically bigger, and these parts can also go higher in voltage as well. And in tantalum polymer technology, the ESR is much lower, especially compared to the wet aluminum electrolytic parts, which means that these parts will see capacitance roll-off occur at much higher frequencies. The life of these will also be much longer compared to a wet aluminum electrolytic part as well, because we don't have to worry about that electrolyte drying out. Lastly, we've got tantalum MnO2, or manganese dioxide, in the cathode of these parts. These will also have capacitance roll-off at lower frequencies. They're stable, but these do have higher ESRs, and these will have to be derated by 50% for reliability, and then additional derating if the application is above 85 degrees C. Next, we've got the different capabilities and trade-offs for various inductor technologies. So first off, we have metal composite inductors, and these are inherently shielded, so there isn't leakage of magnetic flux. These parts also have very soft saturation, so this technology will provide better inductive performance compared to ferrite technology. This saturation depends on temperature. The higher the temperature, the lower the current that it saturates. The downside is that these will have lower inductance values compared to ferrite inductors, and the efficiency will not be as high compared to the manganese zinc ferrites due to core loss. So moving on to the ferrite inductors now. So we've got manganese zinc, which is more prominently used compared to the nickel zinc. And these parts have low core loss, but they do have hard saturations. So the inductance loss will be more drastic compared to the metal composite inductors. This means that you'll need to design a system that will have peak currents below the saturation current at the maximum temperature that the system is operating at. So that concludes the capabilities and trade-offs of the various capacitor and inductor technologies. Now let's briefly go over some fundamentals, which includes decoupling, filtering, and low transients. So first off, what is decoupling and filtering? These two things can be confused and mistakenly be thought of the same, but they do have different purposes. So decoupling is when something is being given up, and filtering is when something is being passed along. And in this example, in this microprocessor block diagram, we have 4 main stages. So first we have the DC input, then we have the DC to DC conversion where that voltage is being stepped down, the voltage regulator module, and then finally the IC. And between all of these stages, we've got decoupling and filtering capacitors to absorb and deliver charge depending on what's needed. So first, we'll be diving deeper into decoupling. So the most prevalent use of capacitors within low voltage DC designs is to decouple an IC from the power supply circuitry. The IC can use this set of capacitors and bypass the power supply if needed, hence its name, bypass capacitor. These capacitors are mounted as close as possible to the IC and essentially act as a local reservoir of energy, which helps maintain a stable voltage level and supply fast power. Decoupling capacitors protect the IC against high frequency noise on the bus, decouple RC delays that contribute to lowering bus levels, prevent the IC from being impacted by a voltage droop that can occur if there are numerous devices demanding power all at the same time. So they eliminate delays in supplying power, which is a critical issue with modern high performance embedded devices, and ensures a strictly regulated voltage that is within the increasingly tight tolerances needed to ensure acceptable operation in today's digital designs. Now, let's discuss impedance. We need the impedance to be on the same level or lower than what the impedance of the target IC is so that it can power our distribution network and be decoupled efficiently. So first, we need to calculate our target impedance, which can be done by applying just another variation of Ohm's law. So, which is this equation here. So we've got the target impedance equals to the voltage rail times the percent ripple over 100, all of that divided by the maximum transient current. So then we'll transform it into the time domain, integrate it, and then subtract out the step response from the VRM. So for this example, our target impedance is 100 milliohms, and the lower and upper frequency bands are 10 kilohertz and 500 megahertz. Now we're starting off with just one 04021 microfarad ceramic capacitor, and we see that we have an SRF of 6.5 megahertz, but our impedance isn't quite what we wanted at our lower and upper bands. So let's take a look at that real quick. So at our lower band, the impedance curve, which is this bolder yellow curve here, is way above the target impedance line, which is this horizontal line here, which is the same for the upper frequency band. So at both the lower and upper frequency bands, these do not meet our target impedance. So let's add another of the same capacitor in parallel. From this, we can see that the SRF doesn't change at all, but we do see that the impedance came down just a little bit within the target frequency band. But we can still see that it's still really far off. It is still not within this targeted impedance threshold line here. Now, we have 10 of these identical capacitors in parallel together, but we're still not really meeting our target of that 100 milliohms impedance. So we can see from this example that we've lowered the impedance, not quite enough to be within the target frequency band. We've reduced the total ESR, and we can reduce the physical inductance by using multiple smaller capacitors versus a few large ones, since the larger ones have higher ESL, and conveniently putting capacitors in parallel doesn't change the ESL. So we can see that we have some benefits already, but modern microprocessors and whatnot demand that we now design our power distribution networks a bit more systematically than just cascading more and more of the same capacitor in order to meet the impedance needs. In this next example, with the same impedance target and same frequency band of 10 kilohertz to 500 megahertz, we'll try to be more strategic with the capacitors we choose to cascade. So first, we start off with a 330 microfarad tantalum polymer capacitor, and it looks like the impedance at the lower bound is below the target impedance line. So it's right here, which is good, but the impedance at the upper bound is much higher than the target impedance line. So what do we do next? We'll add a lower capacitance part. So we added a 1 microfarad ceramic capacitor, and we can see the results of that here. So this dark gray line here is the combined impedance, and we can see that the impedance at the upper bound was lowered just a bit, but it's still higher than the target impedance. Now you can see there's this point here that popped up called the anti-resonant point, which can be problematic as it's higher than, as it can be higher than the impedance of both the initial tantalum part and the ceramic part. So we want to keep an eye on this point now to make sure it's also below the target impedance line at both the lower and upper bound. So next, we added another of that same 1 microfarad ceramic capacitor, and this pushed the anti-resonant point down just a little bit, as well as the impedance at the upper bound. However, we're still not at our impedance target within our entire frequency band. Next, we added a smaller ceramic capacitor of 10 nanofarads to bring down the impedance at the upper bound down even further. However, this now gave us another anti-resonant point to look out for, which is right here. To further lower the impedance at the upper bound, we've added 6 more of the 10 nanofarad ceramic part, which did drastically lower the impedance at the upper bound. However, doing this raised one of the anti-resonant points. So this is now a problem, as this is much higher. Well, this is now above the target impedance line. To lower the anti-resonant point and further lower the impedance at the upper bound, we added a 47 nanofarad ceramic part, which effectively lowered the anti-resonant point. However, we still need to lower the impedance at the upper bound even further. So we added 6 more of those 47 nanofarad ceramic parts, and it looks like all of the anti-resonant points are now below the target impedance line, and the impedance at the upper bound is almost at our target of 100 milliohms. So next, we've added a 4.7 nanofarad ceramic part, and we do see that the anti-resonant points are all below the target impedance now, and the impedance at the upper bound continues to get closer to our impedance target of 100 milliohms. Lastly, we added 6 more of those 4.7 parts and added a bias voltage, which successfully decreased the combined impedance curve of these parts so that it's under the target impedance of 100 milliohms throughout the frequency range of 10 kilohertz and 500 megahertz. And the combined capacitance that we've used is 331 microfarads. So this is basically an overview of what we've just done in that previous example. Our goal was to match the impedance of the processor and decouple the power distribution network. What we did was took that initial 330 microfarad part and added lower capacitance value parts in order to lower the impedance at the upper frequency bound, as well as keeping in mind anti-resonant points. So this example was done on Chemet's KSIM tool, which is a great resource available to simulate various curves such as impedance versus frequency, current versus voltage, temperature rise versus ripple current, and etc. You can choose the parts via the selection tool or input a specific part number if you have a part in mind already. You can also enter the quantity of the parts that you would want and then select the, you also want to select to combine the impedances of every part that you've selected. And lastly, within this decoupling section, this is a real world example of a power distribution network designed by Larry Mosley to demonstrate that as we move closer to the target, as the frequency increases, there are various capacitors that we tend to use. At the lower frequency range, these demand higher cap values, which can be tantalum polymers, aluminum polymers, and even ceramics and film capacitors. And as you move closer to the load and the frequency increases, you need better frequency response, lower ESR, ESL, lower capacitance values as the frequency increases, which generally tend to be ceramic capacitors. The next topic we'll cover is filtering. So the goal with filtering is to block any unwanted signals and pass along the wanted signals. So in this example, let's look at a simplified DC to DC converter. So on the output, we have Cout as well as inductors. We'll go over the key benefits of the different capacitor and inductor types on this slide, as it can be confusing when you start designing your filter caps and there's just so many different technology options. So while each circuit will be different, a general rule of thumb for input capacitors is that for ceramics or films, can be used for input voltages greater than 40 volts, while polymers, ceramics, and tantalums are more suited for input voltages less than 40 volts. So ceramics are pretty good for quick frequency response across pretty much any voltage range, and particularly for lower voltages, since that's where they tend to become more, since they tend to be more cost effective. Films are pretty okay, but if frequency is higher, you might have some dissipation factor concerns. And these are not ideal for applications below 40 volts. And just due to nuances in film materials available, this would just not be the best selection. Aluminum electrolytics are pretty great at low frequencies, but not the best with frequency, since they tend to suffer from the capacitance roll-off as frequency increases, which also means higher ESR. But if one of your driving factors is cost effectiveness, then they're effective enough to function properly across most practical voltages. And then we have the polymers. Aluminum polymer handles frequency a little bit better, than the wet electrolytics, and is also good across different voltages, and they're also cost effective. They also come in smaller form factors and have lower ESR. And then here, when we say polymer, sometimes we'll say polymer just to indicate tantalum polymer. So a little bit of, so tantalum polymers will have a limited voltage range available, but they're pretty good for anything below 40 volts. And they also have lower ESR and better ripple current handling capabilities than its MnO2 predecessor. And then we have the predecessor here, the tantalum MnO2, and these could be better at frequency response, and they're not exactly the best for high voltages, but that's due to the 50% voltage derating that we put in place for reliability purposes. So you might have a 40 volt rated cap, but you'll only be able to use half of that. And the inductors to be used with the output capacitance, basically we have two options. We have the metal composite inductors, which is good up to about 40 amps and has nice soft saturations, but core loss tends to be a little higher compared to ferrites. And then we have our ferrite inductors, which here's our TPI one-turn ferrites, and these are good up to 70 amps, much better. They also have much better core loss, which leads to better efficiency, and it tends to have a harder saturation profile. And just a quick example here to show the benefit of input filtering. So on the left here, we can see where we haven't used any filter caps, and the ripple voltage is 2.78 volts. And on the right here, where we do have a filter cap being used, the ripple voltage is 0.47. So next is our final topic, which are load transients or load fluctuations in the circuit, and we'll go over how to handle such situations. So looking at a circuit for a controller, we'll need a bank of capacitors on our output to act as a reservoir of capacitance for any possible transient events. But first, we're going to calculate what inductor is being used in order to figure out the size of the capacitor bank needed. So to do that, we use this formula here, which is V out times the difference of V in and V out all over the change in current times the switching frequency times V in. In this example, we have V in being 12 volts, V out being 1.2 volts, the switching frequency being 600 kilohertz, and the change in current being 60 amps to 120 amps. And we have these two equations here that takes into account both of the current values. So let's go over these equations. On top here, we have the 120 amps equation. We have 1.2 volts times 12 volts minus 1.2 volts. All of that divided by 120 amps times 600 kilohertz times 12 volts. And this gives us 15 nanohenries. And then the bottom equation takes into account the 60 amps. So we have 1.2 volts times 12 volts minus 1.2 volts. All of that divided by 60 amps times 600 kilohertz times 12 volts. And that gives us 30 nanohenries. And so now we can then use this formula to calculate the capacitance needed on the output, and which is the output inductance times the transient current, times the transient current change squared, all of that divided by 2 times the output voltage regulation times the duty cycle times the difference of the maximum input voltage and the output voltage. Here in this example, we have that 15 nanohenries that we calculated earlier, as well as these provided values here at the bottom. So now we plug these values into the equation on the previous slide. So 15 nanohenries times 290 amps squared divided by 2 times 50 millivolts times 0.111 times 12 volts minus 1.2 volts. And that gives us 10.5 millifarads. So we'll need 10.5 millifarads on our output to act as a reservoir of capacitance in case of any load fluctuation events or low transient events, and ultimately protecting the circuit. So that example that we had just went over was an ideal case that did not take into account ESR. Now we'll go over a few examples that do take into account ESR. So this first example will deal with a 470 microfarad, 2.5 volts DC, 5 milliohms capacitor. So this is almost the same equation that we used to solve for the output capacitance in the previous example, except now we're taking into account the ESR here. So we've got the output inductance times the transient current squared, all of that divided by 2 times the difference of the output voltage regulation and the voltage drop across the resistive component of the output capacitor, times the duty cycle, times the difference in the maximum input voltage and the output voltage. With this new equation, we now have 3 unknowns. So the first being C out min, which is the total output capacitance. The second being V drop ESR, which is the voltage drop across the resistive element of the capacitor. And this is approximately 2 times the total ESR of the bank times the current. The third unknown being NC, which is the number of capacitors in the bank. So now with these given examples, we've plugged them into these 3 equations. With this, we can ultimately solve for the total output capacitance by plugging these 2 bottom equations into the total output capacitance equation. And that would look something like this here. So solving this entire equation will give us the total output capacitance of 37.78 millifarads, which would require about 81 capacitors. So this is what is needed when we take into account ESR. In the ideal case, not taking ESR into consideration, the total output capacitance required would be 10.5 millifarads, which would require 23 capacitors. And that is actually a drastic difference, as taking ESR into account almost quadruples how many capacitors is needed. In this last example, we have that same capacitor, but the ESR is now 3 milliohms instead of that 5 milliohms that we used in the previous example. And this is mainly to show how ESR affects the output capacitance needed. So again, we'll be utilizing the output capacitance formula that takes ESR into consideration. this is the same formula we used in the previous example. And again, we have the same 3 unknowns as the previous example. So plugging in the given values for each variable, we're able to plug the drop ESR and NC into the output capacitance formula here, and that gives us this equation here on top. And solving this would give us these values here circled in green. So the output capacitance required would be 26.879 millifarads, which would require 58 capacitors. So compared to the previous example that had 5 milliohms ESR, this 3 milliohms ESR part will require about 20 capacitors less than the 5 milliohms example. Not taking ESR into consideration is a big mistake, and this could severely mess up a design, which is why it's in red, and the 81 capacitor solution is in yellow, given that solution actually took the ESR into consideration. And lastly, in this final section, we have technology key characteristics. So these are the key characteristics for class 2 and 3 ceramic capacitors, which are made of barium titanate technology. So there are voltage coefficients, which contributes to DC bias effects and AC bias effects. These parts will also experience aging, which means that there will be a change in capacitance over time due to the change in crystalline structure of the barium titanate technology. And aging can always be reversed by bringing these parts above its Curie temperature. And these parts also experience piezoelectricity and electrostriction, again, due to its crystalline structure and dipoles when applying alternating voltages. And one thing to note is that all of these characteristics are not observed in class 1 ceramics, such as C0G parts. And this slide, including the rest of these slides highlighting key characteristics of each technology, will have this hyperlink here, which you can click, and will bring you to our Engineering Center glossary. Next up, we've got tantalum polymers. So these parts do have a temperature coefficient, which is close to about plus or minus 15%. These also have DC leakage. In the data sheets, it's stated that the DC leakage is measured after 5 minutes of it being powered up to allow it to settle and allow self-healing to occur. And leakage tend to decrease over time. So the longer you run the part, the more it self-heals. So DC leakage tend to decrease over time. These parts also experience the RC ladder effect. So as these parts go up in frequency, they will lose capacitance. This also affects aluminum polymer parts as well. And compared to its predecessor, the tantalum MnO2 capacitors, these tantalum polymer parts have a non-ignition failure mode, as seen historically in tantalum MnO2 parts, where those parts would have an ignition failure mode. These parts do not have that because they don't have the MnO2 technology in them. Tantalum polymer parts require 10 to 20% voltage derating for temperature ranges of negative 55 degrees C to 105 degrees C, and additional temperature derating above, beyond 105 degrees C. Next up, we have aluminum electrolytic parts, and these do have similar characteristics that we've already briefly went over for tantalum polymer parts. So one thing to note that is that these do have ESR, and So these parts are extremely dependent on temperature. And as these parts get colder, the ESR drastically increases as the ionic charge in the electrolyte migrates from the anode to the cathode and vice versa. So as the temperature gets colder, the rate in which these ions can move in the electrolyte slows down. And this contributes to the increase in ESR as temperature becomes colder. And again, we've got self-healing and aging. So with self-healing in wet systems, the electrolyte provides oxygen to the dielectric, which reforms and regrows the dielectric. With aging in wet electrolytic parts, the part wears out due to the part drying out as you're consuming the electrolyte as the part is being used. And then we do have two rules for life expectancy. So for every 10 degrees drop in temperature, the life is multiplied by a factor of 2. For every 20 degrees decrease in temperature, the life is multiplied by a factor of 4. Next, we've got aluminum polymer V-chips. And again, most of this is the same as with the previous aluminum electrolytic capacitors. However, the life model is for every 20 degrees decrease in temperature, the life is multiplied by a factor of 10, which is very different from the wet electrolytics. Next, we've got aluminum polymer H chips, and I won't go over these as, again, most of these are similar to the previous characteristics that I had just went over. And with metal composite inductors, the inductance range is limited, and these also have higher DC resistance due to low permeability. These have better saturation compared to ferrite inductors, as these have soft saturation due to the distribution gap. These are also stable over temperature, and the magnetic flux in these parts are inherently shielded. The downside is that these have higher core loss than ferrite inductors. With ferrite inductors, these do have a bigger range of inductance as well as lower DC resistance due to its higher permeability compared to the metal composite inductors. However, the downside is that these do have hard saturation and high magnetic flux leakage, as well as low core loss. These parts are also greatly affected by temperature. And lastly, we've got TVS diodes, where the leakage current will vary over temperature. And the IV curve will shift slightly as temperature varies, and derating these will change the peak capabilities for both current and power. So current and power will decrease as you go up in temperature. And the last point is that these parts have stray parasitic capacitance that you have to keep an eye on. And next we have the summary slide. So this is the summary of what we've just went over, which is an overview of low voltage DC designs using the various types of components, as well as the key characteristics of each technology. We also went over decoupling and filtering, as well as examples for each of those topics. We also discussed ESR in those examples, as it's a critical characteristic to consider when choosing capacitors for low transients. And this last point here points out that capacitors, inductors, and TVS diodes have varying key characteristics, which can change their performance. And these changes must be considered when selecting them for a design. So that concludes everything that we covered today. And next, we'll have the Q&A portion of this Design It Day presentation.